great to be here. I've had a lot of interesting discussions, and it's fun to get away from the forest sometimes. I'm going to tell you about a mysterious thing that perhaps doesn't exist, analytically one-dimensional spheres, and two problems that we were unable to solve, but we were able to connect to each other. This is joint work with Geisy David. So I'll start by trying to tell you what these two problems are. And each of them, they have something in common, but something also they're quite different. So I'll start with the first problem. Okay, so in the first problem, we're looking at spaces that are Q, or we're looking for objects that are Q all first regular. So metric measure spaces x d mu that are Q all first regular. And all first regularity means that the volume of the ball is comparable to R sub Q, where R is, if it's an unbounded space, R is any positive number. If it's a bounded space, then you have to assume that R is less than the diameter of x. Small typo that is in almost every paper on this topic is that you really have to put a 2 there for just stupid reasons, because usually balls are open. So everybody makes that mistake, so but you can ignore it if you want. It's an inconsequential mistake that people make. But okay, the Q all first regular is this. In this case, this mu, well, it's useful for some arguments to actually have that separate mu, but then this means that mu is comparable to the Q Hausdorff measure. So in that case, really, I could say metric space is Q all first regular, and then mu you can choose as so one less data to specify. Okay, that's all first regular. The second one is then a condition that is maybe more mysterious, concerns having a lot of curves in the space in some specific way. So we say that x as d mu satisfies a Q Poincaré inequality if there exists some constant c, 1, such that for every f which is the map, or which is Lipschitz, we can control, and for every ball in the space, the oscillation of the function is controlled. Here the measure is integration is the measure mu by a constant, that's the constant c there, times the radius of the ball, and then some measurement of the oscillation, which in this case is this q. There's about a million ways of writing this inequality. All of them are mutually equivalent when the spaces are complete and doubling. So you might have seen another version of this inequality. I'll dare to say that most likely it's equivalent. And I really don't need to define this actually, because whatever sensible definition of the oscillation you put here, it will lead to an equivalent inequality. But I'll just choose one of the canonical ones that has frequently appeared in the literature. And it's only chosen like this because it's one of the easiest to write on the board. It's not that it really matters for anything, that we'll say later. But lip f of x is limit superior of y converging to x equal to x of how fast, or the slope of f. So the change of f divided by the distance. It's always bound by the Lipschitz constant. But so, I mean, you could put some version of lim if you, well, you cannot put here lim in 0 usually, but you can modify it a little bit. Okay. I mean, this mysterious thing that comes originally from PDEs turns out is a convenient way, one of the equivalent ways of measuring that your space has a lot of curves in it. And if you have both of these things, we call x a Q Lardner space. So I say that x d mu is Q Lardner if it is Q all first regular, which I abbreviate as AR, and it has a Q Poincaré inequality. Word of warning, usually this is not the definition of Lerner that you'll find in the literature. In particular, people use the Lerner condition without the Alfors regularity condition. There's an awkward thing when you do that. If you don't assume Alfors regularity, then Q Lerner condition is not a scale invariant condition. So then it's saying something different on different scales of space, which is something which there are cases and theorems where this is relevant, but in many, like, it's really natural to pair these two together. So for me, the interesting case of Q Lerner is always Q Alfors regular, and that's why I put it as part of the definition. But you might see, if you see this term, you might check whether it's included or not. Okay, so why do people look at this object? Well, before that, I want to give you one example of something that satisfies both of these assumptions. Well, maybe something very simple, of course. Rn is n Alfors regular and satisfies n Poincaré inequality. I'm not going to prove it. But okay, that's a little bit boring. You've done PDEs, you've seen that already. Of course, you could, in place of Rn, I could also have a non-collapsed Ricci manifold with lower Ricci curvature bound. It will also satisfy a Poincaré inequality and Alfors regularity. The non-collapsed corresponds to its Alfors regular. But I'll give you something more interesting, and you might have been to Riku's talk here that occurred at some point in the past. I wasn't here, so I don't know when. But that gives you something that is similar to that. I'll start off with this cross here, and then what I do is I take two copies of this cross and I glue them along the midpoints of these edges. Another way of thinking about it is I replace each of the cross in intervals with a cross. So that one is replaced with a cross, this one is replaced with a cross, this one is replaced with a cross, and this one is replaced with a cross. And I glue them along their right and left endpoints. There are 2 points. I color one blue and the other one red, and I match these together. Okay, that's the first step. You do this again. I don't want to draw it. You can try to imagine it. Some people have done it with more or less success. But you repeat this infinitely often. You get a limit space here, and this is what many people call a Laakso space. Or one of the many things that other people call Laakso space. So, I mean, this is as a set in a sense that I've described it, but there's a metric. What is the metric that you do? Each of these is a graph that comes with a path metric. You have to rescale the path metric so that the diameter doesn't blow up to infinity. Here, I scale it by half, so the distance between this, what is on the picture, left and right hand side is 1. Here, the distance is 1/4, so I divide by. At the next stage, it's 1/8. At the end stage, it's -n. In this way, you get a sequence of metric spaces, and you wave your hands, or take some inverse limit, or whatever you want to do. Actually, whatever limit process you want to do, similar to this constant, that whatever is your preferred way of taking limits, every way of reasonable way of taking limits will produce the same space, and this is x infinity, that is the Laakso space. You'll also notice that this is very self-similar. There are 4 pieces that look exactly the same here. Here there are 16 pieces that look exactly the same. 2 to the n pieces that look 2 to the 2n pieces that look exactly the same. So this is actually a 2 Alfors regular space. Its Hausdorff dimension is 2, and the Hausdorff 2 measure behaves in this way. Actually, you can open up Falconer's book and look at how Falconer proves that this space is 2-dimensional, and that actually gives you 2 Alfors regularity. Or you can open Vigus and my paper as another proof, or you can open Laakso's paper. Okay. This space is 2 Alfors regular, and it also satisfies this inequality. Now, I won't explain you why, but I'll say you one, like I said to you, this inequality means that there's a lot of curves. And where are the curves here? The lot of curves that you see. There's the left and right curves in this picture. Here's one rectifiable curve, there's another. So there's 2 left to right rectifiable curves here. Here there's 4. Well, not just 4 really, because you can always choose to go up or down. at every intersection point. So there's a whole family that actually represents the measure in a nice way. That goes with it. And it doesn't just go from left to right, because if you can go left to right, everything here looks similar, so you can actually also go from one edge to another. You can lift paths in this procedure. And that gives you, this is what this is really saying. Anyway. Okay. Great. You can play this game of finding new examples of spaces that satisfy inequality. Some people have done careers with that. But why do people care? And this emerged in the 90s. Well, this is related to quasi-conformal mappings. Quasi-conformal and quasi-symmetric mappings. So a mapping between two metric spaces x and y, a homeomorphism, is called an eta quasi-symmetry if the following condition is true. Whenever you have 3 points in x whose distances are related in this way, so y is, you think as y is being closer than z, and t is measuring how much closer it is. This implies that the image points are eta equals. And what is eta here? It is called a distortion function. It's some homomorphism, so because of the way this is defined, 0 has to be on 0. This has to be an increasing map. So what this form means that, so on the main side, I mean, I should think of y as being closer than z, because this doesn't matter, t can be 10, so it's not, it's closer or really not too much further away. But let's just simplify a little bit, lie a little bit, let's say it's closer. And this means that on the image side, you're not too much further away, or really again. Now, if this is a homomorphism, once t is small enough, this actually forces it also to be closer. Quantitative relationship. Okay. You'll have seen a definition where this is written with a ratio, but I promise you I have a point why I write it you like this. Point that is kind of trivial, but for some reason nobody has really explicated it. Okay, so the big thing of quasi-symmetric maps is the following theorem of Hain and Koskela. This theorem was first proved very first, it was proved in the plane, and was proved in higher dimensional Euclidean spaces and manifolds. Then Hain and Koskela extended it to Carnot groups, and the big breakthrough in the field that really launched analysis on metric spaces was this theorem that was for Lerner spaces. That was the reason why this definition became, at least in this context, came into prominence. Earlier, there had been other reasons to look at it. If x and y are Q Lerner spaces, and you have a mapping that is quasi-conformal. I don't define this now. It's an infinitesimal version of this quasi-symmetry condition. Then this is equivalent, and this is a well, that's a background assumption. It's equivalent to F being a quasi-symmetry. So this is some sort of a regularity statement, local to global result. This is an infinitesimal condition, this is a global condition. But maybe what has often more consequences is an implication of this. This was maybe observed later. Would be the best person to attribute this to. I think this was seen by a lot of different people. Kleiner had an argument for this. Jeremy Tyson, Nageswari Shanmugalingam, and Pekka Koskela also had an argument for this. but F is, in a sense, differentiable almost everywhere. Whatever that means in this kind of a general metric setting. And this fact, this differentiability almost everywhere, is the reason that, and this was alluded to by in the lectures that we heard earlier, why this is relevant for Hausdorff rigidity, especially this differentiability conclusion, because when x and y are spheres, and I should say here 2 is greater than 1, because it's relevant for this example, then what this example tells us is when n is greater than or equal to 2, so once we have at least 2-dimensional spheres, then quasi-conformal and quasi-symmetric maps are differentiable almost everywhere. And here, so you might have not know what this means, but this is just classical differentiable almost everywhere. The blow-up of the map is a linear map in the tension space. And this is one of the steps that you can use to prove Hausdorff rigidity, for example, because this Sn you can think of as the boundary of hyperbolic n-1 dimensional space. Okay, so this was, well, this gave Hausdorff rigidity, and there was a hope maybe that this kind of strategy could be used more generally for hyperbolic spaces, for hyperbolic groups. Well, what is crucial here, what people thought was crucial here, was that there were 2 objects here. There was a hyperbolic space, or in the case, really a hyperbolic group, and there was, on the boundary of it, however this is defined, there's a Loebner structure. And this cannot be any Loebner metric. This Loebner metric has to actually be quasi-symmetric to what are called visual metrics. So this is exactly what happens in this Hausdorff rigidity setting. We have so where does the group come from? Well, the Hausdorff rigidity concerns a compact manifold, so the group is the fundamental group of that manifold. The boundary, the visual boundary of that group is the same as the boundary of the universal cover, which is Sn. Now this sphere comes with 2 different metrics. It comes with the cat-1 metric, which is the usual round Loebner metric that we know, and from the hyperbolic Grommel's construction that also comes with a so-called visual metric. These are not the same. Actually, if they are the same, then, well, yeah, they're never the same. They're never the same. But they're always quite symmetric to each other. So there was a hope expressed by a number of authors. Juha Heinonen, Bruce Kleiner mentioned it in his ICM address. A number of other people alluded to this. Kapovich wrote about this. And that could, what are the examples of groups where this wonderful thing happens? So they're hyperbolic and their boundary has a Loebner metric. And there was so what are examples where this happens? Well, of course, so geez, any pi1 of a hyperbolic n manifold, okay, n is greater than equal to 3. Wonderful. That gives us a lot of examples. Then there's also lattices, co-compact lattices, or we'll have to say, yeah, co-compact lattices in rank 1 symmetric spaces. In those cases, the boundaries happen to be Carnot groups. So another setting where we understand things. And that's the only two examples that existed for a while. Except, so if this was the case, then kind of it would really look like this is a very limited special case. But then Bourdon and Pajot found more examples. Well, this is their example. You can realize it as a boundary of a group, but in that case you can also equivalently realize it as a boundary of a building. This corresponds to, let's say, something equal to a hyperbolic building. Hyperbolic ocean building. That picture I drew there, that's how you should think of the boundary looking like. But actually, it's not, that exactly is not a boundary of any hyperbolic group. You can actually prove that, that's not a group. But a picture very similar to it. So there you have one replacement rule, here you have to have finitely many replacement rules that you follow with a certain pattern. But anyway, if we'll look, it will be homomorphic to that example, and from the perspective of analyzing it, it will look very simple. But that's that is. So there's one extremely classical one fairly classical one weird one, and that's it. So the question was, are there others? Like, is this the limit of this method? And still, 20 years on, actually, this remains the only example on the list. So, motivated by this, I mean, one could ask, in general, like, these seem like special cases, but like, could we understand even in general, given a metric space, xd, when is xd quasi-symmetric to a Wagner space? This seems like a special case. Maybe we can actually, or perhaps a beautiful case would be if we could find some very weak sufficient condition for it, and then we could find more groups that satisfy this. Bourdon and Kleiner tried this.
Are there simple examples of hyperbolic groups such that the boundary is not?
I'll soon give some examples. I mean, not group boundaries, but like there will some phenomenon that will prevent it. Yeah.
There is a very basic question. How do you put the measure on the boundary of G?
So notice, so that refers to this one. The metric is always Alford's regular. So it's the Alford's regular measure. There's also another construction of the measure in that case. But since the metric is Alford's regular, we'll use that measure.
So the measure is always the Hausdorff measure?
Yes, yeah. But notice, so I mean, we're looking for, the visual metrics are not the right ones. They're never the right ones. So you have to always quasi-symmetrically deform them. Actually, in the Bourdon-Pajot examples also, it's not a visual metric that they construct, it's a different metric that will attain its control, that will be quasi-symmetric to a Loevner. But the metric is always Alford's regular, and the measure will be the Alford's regular. So, yes, and there's a convenient way of, so here, there's superficially two different spaces, but because they're homomorphic, the only thing that is really changing is the metric, because y is always isometric to x with the pulled back metric. So for this reason, this question actually can be expressed in terms of what is called the conformal gauge of x, which consists of all the metrics d prime, such that xd is a quasi-symmetric to xd prime, or the identity map between these is quasi-symmetric for some eta. Eta quasi-symmetric for some eta. And now a homework question is to show that, and this is a thing that for some reason nobody has written out anywhere, but it's a trivial observation, that this is a convex cone. It's trivial from this, because this is a linear inequality on the metric D. So this set is defined. The eta quasi-symmetries for a fixed eta are defined by an uncountable set of linear constraints. So any set defined by a kind of group of linear constraints is a convex set. And if you multiply a metric, it's still conformal to the original, so it's still it's a cone. So this is a convex cone. It's not compact. Of course, you can scale things down to 0. But for a fixed eta, that's the only thing you can do. It's actually compact, as long as you stay away from 0. But yeah, actually, we use this observation with Gaussian data. I mean, this has other implications, like the space of quasi-circles is a convex cone, has some linear structure to it, which is maybe not so apparent if you think of them as curves in the space. Like, how do you add two curves in the space? You can add you can pull back the metrics, add the metrics, and that makes the convex space. So if you look, this is actually a nice thing I like to advertise for these people. So for some reason, this elementary fact was not written anywhere. Okay, so in this way, you can think of this metric question here asking us, when is there a metric here that is Alford's regular, and that is when can you find a metric? Okay. The motivation for this in particular was this, that if we could find more groups in this category, group boundaries in this category. Still, there are no new ones. Okay, so this is all about problem 1. The story of problem 2 is quite a bit shorter, unfortunately. It starts off with 2 very similar conditions. So instead of all-force regularity, we're looking at doubling measures. Mu is doubling if if there exists a constant p such that mu of twice the radius is less than a constant time. My volume, of course, my measures are always non-zero. Nothing interesting in 0 measures. So that is a significant weakening, of course, of the Alford's regularity condition. And then we also just have the 1p Poincaré inequality, or the p Poincaré inequality, which is just you replace q with p in upstairs there. I mean, I do this switch to the exponent p just because, like, now there's no, it's not q Alford's regular, so it's reversed. Okay. So, of course, anything that was, those examples are still there. There are some more examples as well, but yeah. Now, there was a question here that, okay, there are many examples of these. In fact, like already we saw some examples, regular ones. But we could ask, what are the possible metrics and measures on Euclidean space or a manifold? I mean, here this is just the simplest n manifold. That make this PI space, and that makes this D doubling. Like, how many ways can we make a manifold into a multiple? It is quite not so hard to see that there are all sorts of weird constructions like the one I drew up there that give you PI spaces. But what if you have force to be homomorphic to a manifold? Does that restrict this somehow? Is there something that you cannot do because you have to be homomorphic to? And this is still quite open. I will say some things about this. But one thing that is very mysterious and that we actually don't understand at all yet, well, almost at all, is what are so possible analytic dimensions. And I will tell you what analytic dimension is. So, we say that actually mu, metric measure space, has analytic dimension at most n if for every n tuple of Lipschitz functions and almost every point in your space, mu almost every point in the space, there exists some scalars along the n, not all 0, such that a linear combination of my functions, so sum of from I1 to n, 1 to I of fi y minus fi of x, it's not quite 0, but is 0 to the first order, so little o of the distance between the points. So this could be, you should think of this as this vector consisting of these components is linearly dependent up to a smaller order. So if you divide by the distance, it goes to 0. I mean, you have to have some error. So if your X is Euclidean space, then Rademacher's theorem tells you that this is true whenever capital N is greater than or equal to n. No, it's strictly greater than n. I should say less than, strictly less than n. So not every, so most spaces that you will think about will not have finite analytic dimension or bounded analytic dimension. And in fact, if you find this thing confusing, you can only focus on the case capital N equals 2 here, because then you only have 2 functions, and then they have to just be linearly, those 2 functions are linearly dependent at almost every point. And so here, there's a strict inequality, but just like with topological dimension, we define a notion that space has analytic dimension d if it has analytic dimension less than d plus 1, and that's the smallest constant for which it has analytic dimension less than that. And now, a funny way of expressing a famous theorem of Jeff Cheeger is that if actually mu is doubling plus you have this Poincaré inequality, then you have a finite analytic dimension. So actually, almost give another talk about this. It is almost an if and only if statement, but it's quite mysterious. Your Lipschitz differentiability if and only if you have finite analytic dimension. So a lot of spaces don't. So this question really that I have here, one way of casting what I mean by how weird structures are and can have, is that is it true that if you have a two-dimensional space, a two-dimensional manifold, my title, so let's say spheres, is that does there exist a metric measure manifold as 2 that is analytically one-dimensional? So where every pair of Lipschitz functions is dependent in the sense of these Lipschitz functions are measuring directions. They are elements of the cotangent space. There's only one-dimensional cotangent space in any pair. well, I raised my other question, but this question and the question of whether you have a quasi-symmetric metric in your conformal gauge, these two things don't seem to have anything in common directly. Now, now there are some spaces where we'd expect that this somehow seems more easier to believe that there are some weird Lochner spaces because we have so many weird examples. This one seems believable, but this one really defies at least my intuition a lot, because if you have something topologically two-dimensional, this is forcing it to be in some sense one-dimensional, but these are really fighting against each other. How can that happen? So this one, I don't believe in this one, but I'd like to believe in that one. I'd like to believe that this one has some nice non-trivial examples where this is true. Okay, so this, I should say also that this notion of analytic dimension is very poorly understood. There's very few theorems. Actually, this kind of definition even hasn't appeared in a very clear way. So I will...
So can I just remind me what is, in the second question, what is that symbol where d prime is supposed to be in what?
In the conformal gauge. This is the conformal. This was all the metric.
So a metric that is conformal.
Quasi-symmetric to my initial metric, that is Lochner. How can I characterize it in terms of data from this space when there exists a...
Isn't the X also like kind of free? What is X? Is X a fixed state?
X is a fixed space, yeah. Well, so...
But which one?
Depending on how ambitious you are. So it could be, if you want to be God, then you say, I give you a space and you answer this question to me. So what is it? What are the metric, can you give metric conditions, a finite set of them that you can check, so that if they're all true, then there exists a metric in the conformal gauge. But we don't understand this question even for specific examples. So if you want a very difficult one to think about, then this is open even for the standard 1/3 Sierpinski cartilage. One thing. For a host of, and I'll give another example.
Okay, so this second question is not on the sphere at all.
No, it's not. It's not.
Okay.
For general, yeah.
Okay, I thought kind of it was metrics.
But it's on different space. And of course, for most XD, this question has nothing to do with this one.
Okay.
But I will give an example of a space where actually this one is connected. Okay. In a second. You'll see why it's connected. So I wanted to give some intuition about analytic dimension. So Rn has analytic dimension n, which follows actually from Roddy-Macher's theorem. Okay, so that's good. And manifolds with the usual volume measure, Riemannian volume measures, Riemannian metrics. They're all analytically n-dimensional if they're n manifolds. And the example that I drew there, this weird space, this is analytically one-dimensional for the reason that there's really only one direction here, left and right. You can make this precisely. But that's the prime cause for it. Turning it into a proof, of course, is not at all trivial. So these Laakso spaces are analytically one-dimensional, and then if you happen to know what is the Heisenberg group, then the Heisenberg group is, as people will like to tell you, it's 4 Alfors regular, it's modeled on R3, it's topologically three-dimensional, a manifold, but it's not by Lipschitz to a Riemannian metric, and it is analytically two-dimensional. So topological dimension is 2, and the analytic dimension. In general, for a Carnot group, this will be the homogeneity dimension. Well, this is more for whatever dimension you have to have have model it on Rn, and this one will be the dimension of the horizontal tangent space, horizontal space. So, of course, with this, you can make you can make these arbitrarily large while keeping this 2. So-called filiform carbon groups. We'll give you examples of that. So this already indicates that this question is not trivial, at least once you have 3 dimensions, because in 3 dimensions you already have 2 very different constructions. There's a Heisenberg group and R3. This one is actually asking whether in 2 dimensions you can have very different constructions. And in 2 dimensions there's only one cardinal group, so there's only one R2, so actually this doesn't give you different examples in R2.
Well, on R2 you can find a distance and a measure which is analytically one-dimensional.
I don't know, but that's...
No, my question is why you study S2, just as something homomorphic to S2?
Because, so if the small, so in 1 dimension there's only one PI structure because it has to be rectifiable, so it's just a line. In 3 dimensions we know that there are different structures. 2 dimensions is a big question mark. We don't know if there's something different from Euclidean space. And that's actually, by a result of Dotting and Kleiner, it would have to have this weird property. Okay.
And there's sort of no difference if you're studying S2 or R2.
No, there's not. I mean, I could put here a square. I can put R2. There's really no difference. I mean, I can glue 2 squares together to get S2. I can roll up S2 to get R2. It's like formally these aren't going to be the same question.
These terms also have everything. There's possible is quasi-symmetric too.
At this point, everything, just any metric, yeah, it could be any metric. As we will see, actually, much more restricted versions of this questions are open, so, yeah, we'll get to your comments shortly. Okay, so Emanuel asked earlier, so now these are the 2 questions, I want to draw some connection between them, and that will, if we look at a little bit at this question, and return to a Emanuel's question, it will be maybe a little bit clearer. So there are some simple situations where we know an answer to this, where we can actually, so given a metric space, we can answer it. And I'll draw 2 such cases. So the so-called Laakso dominant space. You imagine you repeat this be often just in the same way as you did there, except this one time there are cut points in this thing. Points that disconnect the space into components, locally and globally. So here, this point will always disconnect the space into parts. And if you are Q Alfors regular and Q Loebner, here usually emphasize Q is bigger than 1, then you cannot have cut points. So in this case, this is not quasi-symmetric to Loebner because there are cut points. So whenever you have cut points in your space, even a single cut point in your space, then you're not quasi-symmetric. And some groups do have such either cut points or some other similar disconnecting sets. And then that immediately concludes this. So, okay.
So it can't be Q loner for any Q.
No, and no matter what metric you choose there. It is a PI space, so there's a measure that is doubling and satisfies the Poincaré inequality, but it's not Alfors regular. The key is that.
So the point is there is like only one curve going through that point, and that's not enough.
Yeah, well, you could think there, yeah, it's maybe a bit more complicated, but yeah. So this is just not there. You can answer trivially. So sometimes for group boundaries also you can get such a trivial answer to this question. Another setting that is maybe a little bit less trivial is that if I take the unit square, so like a sphere here, and I put there in the x direction I have the Euclidean metric, in the y direction I snowflake the metric. So this metric, there are a lot of rectifiable curves. Actually, a curve is rectifiable if and only if it is horizontal. If it changes the y coordinate, its length is infinite. In this case, you don't run into this problem. There are no cut points. It's homomorphic to the plane. But it's still not quasi-symmetric to Loebner. And the reason for that is much more subtle, but it's related to the fact that the curves in the different directions behave in a different way. If we are traveling horizontally, we have a lot of rectifiable curves that actually give you what's called an Alberta representation. But in the y direction, there are only very long curves. And this means that the x direction, from the perspective of, say, quasi-conformal or quasi-symmetric maps, behaves very differently from the y direction. There are many ways you can make this precise, that they behave differently. And in Loebner spaces, I mean, this condition is scale and location invariant. It's saying that all directions behave the same. This really fights against it. So this means that the reason that you're not quasi-symmetric to Loebner is that you're not directionally homogeneous. Not all directions are equal. Here, you have some annuli that behave in a bad way because of cut points. Here, you have some pairs of balls that behave in a bad way. So they're actually, like, to make these two things rigorous, there are capacity bounds. One is related to capacity of annuli, one is related to capacity of balls, and these examples break the lower bounds for some pairs of balls or some annuli. And these are the reasons why they're not quite as symmetric.
Can I have a question? I feel like you probably can. If you have this space, you can make a function that's non-constant, but the lip f is 0 everywhere.
That's right. It doesn't satisfy Poincaré.
So that immediately that's broken.
That already tells you that this metric does not satisfy Poincaré. But there's no other metric. You cannot deform the metric into something that satisfies it.
In a
Quasi-symmetric way.
Yeah, okay.
Of course, you can like deform it in a drastic way like this, which is not a quasi-symmetry, but this will satisfy Poincaré, but that's not allowed.
Okay.
So you're right, yeah. So in both of these cases, actually, the standard metric does not satisfy Poincaré if you put the upwards regular measure. In this one, you can fix the measure; it will satisfy. Here, there's really nothing you can do other than you can really rip apart the space.
Is this fact that whenever I replace it with any quasi-symmetric metric, there will still be a function which is non-constant and for which lip f is 0?
That's right. Exactly. Yeah.
Is this a property that is generally stable under quasi-symmetries?
No. I mean, in some cases, there can be one where it's not. Yeah.
Oh, okay.
Yeah. So, I mean, there are cases where the answer is yes. I mean, if you Google what is called a Meyer-Snow sphere. So you take a square, you remove the middle, you attach the cube, remove its bottom, and you repeat this infinitely often. It's called Meyer-Snow sphere. Here, like your question would say, it is Q alpha regular for some Q bigger than 2. It does not satisfy that inequality. So there are some weird functions where lip is 0 and it still oscillates. But nonetheless, you can quasi-symmetrically deform it. In fact, you can quasi-symmetrically deform this space into the sphere, or if you just took the top of it into the square. So there's a quasi-symmetric mapping of here to here, and this is 2 alpha regular. Okay, so here you don't. Quasi-symmetric maps don't behave well with, like this inequality is not preserved under quasi-symmetries, actually.
I understand the inequality. I'm just wondering, like, this seemingly stronger proposition that there is a non-constant function for which the thing is 0 is also not stable.
No, sorry. Okay. So I have to get to my punchline. So there are some simple ways that you can fail to be quasi-symmetric to a Loebner. Now, like you heard the talk by Guantila that there's this magical condition called the combinatorial Loebner property, and you could think of the combinatorial Loebner property as being an effective way of saying that neither of these two things happen. They are homogeneous, and they don't have cut points in any good way. And Kleiner conjectured that if your CLP and self-similar, that these two together would imply that there exists a metric in the conformal garden. These would be sufficient conditions for you having a larger metric in the Koch. But so are these, in a sense, are these the only two enemies that you have to fight against? And the interesting thing here is that this condition is something that is checkable in terms of just the metric, and there are many groups that satisfy this. Many groups for which we do not know this answer yet. And I was fascinated by this question. I mean, this is my version of was originally my version of this question. Really, this is a more general. This is a specific version of that. And this turned out to be false in general for some. So with equal, we found counterexamples. But they are very specific counterexamples. So, for example, every other example, such as the boundaries of groups or Sierpinski carpet, they did not resolve it for these spaces. In parallel to this work with Riku, I had this project with Guy that tried to come up with a different example of this, with an entirely different strategy. And you could think of it as, let's try to take the simplest example that looks like this but doesn't break either of these conditions. And the simplest example that I could think of is you take a square, you divide it into a 3 by 3 grid, and you double the central square. Here you can think of it as you're dividing it into parts and you're doubling this middle part. What if you just do this in 2 dimensions? The point of doing it in 2 dimensions, there's actually 3 points. One point is that this way you don't have cut points, so that you don't have this problem. Point 2, this has a dihedral symmetry group, so you don't have this problem. Okay, so you've taken away your 2 enemies. Actually, with Riku, then we show that it has combinatorial Leibniz property, but giving it a general framework where this falls into, in which everything satisfies CLP. Okay. This was maybe almost known, but this example wasn't focused on for some reason. And the third reason I'm interested in this case is that this looks just like that picture looks like a boundary of the Bourdon-Pajot group. This picture is very similar to a boundary of a 3-dimensional hyperbolic building. So my dream would be to actually say that at least, like for some boundaries of hyperbolic groups, that the answer here is no. But the methods that Anttila and we came up with are too weak because those group spaces don't arise as group boundaries. I think you can even prove in some cases that they do not arise as group boundaries. So I wanted to come up with group boundaries that would satisfy this, but they're always more complicated, and my knowledge of group theory is weak, so I came up with a simpler model, this double square. But I'm really thinking, okay, if I could solve this case, I could extend it to this 3-dimensional case. Okay, and why is this interesting? Because for the simple fact that there is a map of this back down to the square. And the map is obvious. You identify the 2 squares to each other. And the theorem that Guy and I showed was that you take this space upstairs, and you take this space downstairs, which is just a square. Okay, you could think of it as a part of a sphere if you want, but and we showed that if X is quasi-symmetric to a Leibniz space, so if the answer to this version of this question in this particular case is true, then there exists a metric and measure on y, so it's on the square, such that the following sequence of things should be true. So let's call y is equal to this square with this metric here. Mu is dedoubling. You have a P Poincaré inequality. You are purely unrectifiable. Two unrectifiable. So all the two rectifiable parts have mu measure 0. You are analytically one-dimensional. And then the thing that Eiko was mentioning earlier, this metric is not something super weird. Well, it is weird if it exists, but it's a little bit less weird than it could be. Namely, D is quasi-symmetric to the standard metric. And yeah. So with the thing above, I'm willing to accept that it's true, but the second thing, I just can't accept it to be true. It cannot be possible. I don't know how to prove it's not possible, but it should not be true. So something's got to give. One of my intuitions is wrong. And I think my time is pretty much up. Maybe I'll say that there's two very nice techniques here. And when we do this, which was very much like this. Two techniques. And both of them I've mentioned in this talk. One is symmetrization. So if this is quasi-symmetric to something Leubner, then on X there's this symmetry group that flips these two pillows. But there is no reason for this new metric to be for this to be an isometry in the new metric. I mean, abstractly, it's just something quasi-symmetric to the original one. It doesn't have to be symmetric. What we do is we symmetrize. If there exists some metric in the conformal gauge that is Leubner, and let's remember the conformal gauge is a convex cone, then we can symmetrize that metric. That will still be quasi-symmetric to the original, because it's a convex cone. It will now be symmetric. There's an annoying technical issue that it's not necessarily Q alpha regular. But after a blow-up argument, it is. So we have to do an intuitive blow-up argument to make it Q alpha regular. Okay. After we've made it symmetric, then we can push forward the measure and we can pull back the metric. Because we cannot push forward a metric. It categorically goes the wrong direction. But you can pull back along these sheet maps. You lift this up to any of the sheets. And because it's symmetric, it doesn't matter what sheet you lifted. You get a metric downstairs. And that gives you the metric field. You can use some general nonsense and then to prove these first two properties. There's some nice work that actually Guy did originally with Jeff Cheeger that's using. And where do these properties come from? And that's the second tool that is quite nice, namely it's differentiation of quasi-conformal maps. And this idea really is one of the steps that is very analogous to Monster rigidity, which is why I really like this argument, is that you look at this space. If this was rectifiable, some positive measure set would be rectifiable, then you could blow it up and this would become Euclidean. But then you remember that there's really another copy of this thing. There's the standard version that you can into form. And this Euclidean thing is quasi-symmetric to the standard one here. But now you have a quasi-symmetry between two standard Euclidean things. And a quasi-symmetric map between two R2s is differentiable almost everywhere. So you blow it up again. So this is like the fifth blow up that we've done. After this fifth blow up, this becomes a linear map. But if this map is linear, it means up here you have a bi-Lipschitz map. But if this map is bi-Lipschitz, these have the same dimension. And that's not possible, because then this would be Q Loebner, and it's not. We can prove that directly. So there's another one, differentiation plus blow-up argument. So it's like similar to Moscow. One of the steps in Moscow rigidity, we use that to show that the rigidity of these sheets implies that this structure here, if it exists, has to not be the standard one in any way. That tells you it's purely true and rectifiable. This analytically one-dimensional thing comes from a guy's work with Bush-Kleiner. And this comes just from the machine. Thank you.
More questions for Sylvester?
Sorry. Just in the definition of analytic dimension, analytically less than n-dimensional. I never worked with anything like this, but there is one dimension I once considered that was very similar looking in the, I think it would be something like, instead of finding the lambdas, instead of being able to find this for every f1 up to fn, you would for every f1 up to fn and every epsilon find like f1 epsilon up to fn epsilon, which are very close, and then you would have that property for those, which would be like slight weakening. I was wondering if this is something you've ever thought about, or if you know what it like means.
Oh, like you mean that you can approximate with functions that satisfy this property?
Yes, but you need to be able to have arbitrarily good approximation.
Yes, I haven't really considered that, but that would correspond to this fragment west chart dimension that we do with Eleftherios Sultanis.
That's nice, because I had it in a completely different setting.
Yeah.
So
we don't say that in the. I think we just fall short of saying that, but like you could. Yeah, I think it should be possible to. Yeah.
okay.
The difference. It's a little bit cheating the way I define an analytic dimension, because if you look at it carefully and you know the topic, then I've baked into the definition that you're a differentiability space. If you're not, actually you're a Lipschitz differentiability if and only if you have finite analytic dimension. So, like the issue with, that's why I don't need to approximate. Like, there is no, the approximations are needed because there are, for any metric space, there is a notion of a tangent space in your sense that measures the directions that are rectifiably accessible. Saying that you're finite analytic dimension, or saying that equivalently saying that you're a Lipschitz differentiability space, is saying that that's it. That there's really no other direction in the space. I mean, that's strictly speaking not true. Like in this case, your only rectifiable direction is the x direction here. Of course, there is some like ghost of another direction in the other direction, but like you can connect things efficiently in that direction by traveling horizontally. So it's not, in the plane there are really two independent directions, like x and y, and you cannot just travel in the x direction in order to, you have to make some angle at some point. You can zigzag, but there's still an angle that's less than pi. So that's what to me means to be Lipschitz differentiability, but your question asks about these cases where you have these approximations. That kind of, in my mind, is a setting where you have some directions here that are not rectifiably accessible.
Yes, that's what I'm.
And that means, of course, that the rectifiable curves don't control them. And that's exactly like this snowflake, Rickman, this kind of thing.
So then you would expect the analytic dimension to be the number of the directions in which you are rectifiable.
That's right. Yeah.
Okay.
So there is a different notion of analytic dimension that would be measured for this chart, and that would your way of saying that that you can, any Lipschitz map you can approximate arbitrarily well with uniformly bounded Lipschitz constant, so that you have them linearly independent, and that would measure that dimension. But it's So Yeah. In the Lipschitz differentiability case, there's no difference between the two.
Any other questions?
So if you remove the condition that the metric would be quasi-symmetric to the regular square, do you think something could exist? Besides that satisfies all the other conditions, but not quasi-symmetric to the square.
I don't know. At present, I don't, yeah. I don't know any way actually of using this condition. Like,
Without that condition, it's very similar to, like, would be comparing R3 to Heisenberg group. Or
yeah, so, okay, that's one. So, I mean, this is, here it's really crucial that we are in 2 dimensions, because if we were in R3, then we know that there is at least some exotic, there's something weird happening. In R3, we know, in R3, we do have 2 different metrics. We have the Euclidean metric and the Lebesgue measure, and then we have the Carnot metric, the Heisenberg metric, and still the measure actually stays the same, but this is analytically 2-dimensional. And this is analytically 3-dimensional. And this is purely 3 unrectifiable. You don't have any 3-dimensional parts in this. But a thing happens here that these are not quasi-symmetric to each other. So, like, you could actually ask in 3 dimensions, does there exist? I mean, I don't know, it's probably harder. In 3 dimensions, does there exist a metric that is quasi-symmetric to the standard one? That makes this a PPI, and that is purely 3 unrectifiable.
So we mentioned in our paper that if you do this with a 3-dimensional cube and you double the center, then what you get is you get an example of something that would be like this. I don't think that either exists, but I have no idea how this condition would be useful. And to make matters worse, with Enrico Ledon, actually we have given them, this is still ongoing work, but maybe in the coming weeks it will be online. In R3, actually, it's not just like Euclidean and Heisenberg. These are not the only 2 things. There's a massive number of these things. Like for any q between 3 and 4, actually, in this case, there exists a metric so that when you equip R3, you equipped it with this metric dq. This is now q offers, and this is Lebesgue measure. Just Lebesgue measure in these coordinates. This is q offers regular and q Poincaré. Actually, it has 1, 1 Poincaré. Isoparametric inequality is true in this case. And it has analytic dimension 2. And to make things even more confusing, in defining this metric, we use the Weierstrass function. So it's a very fractal-like. I mean, in some ways it's very simple, but then the metric is doing some weird nonsense. But it still satisfies all these nice conditions. So in once you go to 3 dimensions and higher, there's a really zoo of PI manifolds. There's like, if somebody walks up to you and says that like they're trying to classify these spaces, you can declare them insane because it's just impossible. So it's too many of them. It's like trying to classify all alpha Holder functions, like alpha bipolar functions. It's just not reasonable. But none of these, of course, are quasi-symmetric to the standard one. So maybe that is the key, but I don't know how to use it. It would be beautiful if somebody came up with a way to use it.
All right, let's thank Sylvester again.